Hopefully this is going to be a little bit of a review for you guys going back to physical science, whenever you took that, whether it was 8th grade, 9th grade, 10th grade. We're going to take a look at light. I'm going to read a quote from Edwin Hubble of the Hubble telescope fame, and it says, "Equipped with his 5 senses, man explores the universe around him and calls the adventure science." And the reason that we mention that is because one of our 5 senses deals directly with light. What are the 5 senses? They are sight, hearing, smelling, tasting, and touching. Obviously, the only one that really works with astronomy is going to be sight. And what do we use to see? We use light, which is why we are covering it in astronomy class. We can only use these 5 senses, even though there are other things out there. You can't feel a magnetic field. You can't feel ionizing radiation. You don't even have sensitive enough feeling to feel the very smallest of earthquakes, even though many animals can. We also can't see with our eyes outside of the visible part of the spectrum. And the visible part is just a little tiny strip of the entire electromagnetic spectrum. So most light is actually invisible to us. We can see that little tiny strip of light, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. We can feel infrared as heat. Ultraviolet radiation, we can kind of feel that on a delay. If you go to the beach and you lay out and you get hit with a bunch of ultraviolet radiation, then a few hours later, you're going to feel that as a sunburn. And the person who actually named Roy G. Biv, the person who studied light and realized that white light can be broken down into different parts of a visible spectrum, none other than Isaac Newton.
Is this your glass? I was like, I'm just even surprised.
Unfortunately, we can't see any microwaves, any radio waves, any gamma rays, any X-rays, only visible light. Which is why we depend on telescopes and other scientific instruments to help us see things outside of the visible part of the spectrum. If we could see the entire electromagnetic spectrum, we could see things like black holes. We could see the cosmic microwave background radiation, which we will get to later this year. We could see the center of our galaxy. Apparently I need to move that. We could see the center of our galaxy. And just so that you guys can kind of have an idea of what I'm talking about, M81 is one of the spiral galaxies that is in our local galaxy cluster. And with visible light, this is what we see. However, when we look at ultraviolet, we can actually determine a whole lot more detail because we don't have quite as much gas and dust blocking our field of view. So we see a much different galaxy when we look at that galaxy outside of the visible part of the spectrum. With that said, we're going to play a little game. You write down what you think you see, and then we're going to change to different parts of the spectrum. So looking at this object in visible light, make a guess. What do you think this is? Now we're going to take a look in ultraviolet. Infrared. We're starting to see a little bit more information. And what is the planet that is on its side that does have rings? This is Uranus. This is another object up in space. What do you think this is? It's not a space lizard, in case you were wondering. We're going to go from radio waves to X-ray. Now you can see the overall shape, and you can see that there's something going on at the North and the South Pole. Now you can see a little bit more detail. Infrared, you can start to see some temperature gradients. What do you guys think it is now? And finally, visible light, hopefully that is very recognizable. This was Jupiter. We're going to do one more. If you look at radio waves, we see this. Infrared, we get a little bit more detail. Visible light, it actually just kind of looks like a fuzzy cloud. If you zoom in from far away, still using visible light, you can see a little bit more detail. This is actually what's known as the Crab Nebula. It is the leftover remnants of a supernova. And the supernova left behind a neutron star, which you cannot see with visible light. Neutron stars give off X-rays, and with X-ray you can see that there is in fact an object at the center. So had we not had an X-ray telescope, we never would have seen that. The Crab Nebula is about 6,500 light years away, which means when this star went supernova, the new bright star in the sky was actually brighter than the moon at night. And you could go outside and you could actually read a book from the light of this supernova. So it was seen by everybody across the entire planet, and it was recorded from places in North America to Asia, Australia, Africa. The place that it wasn't written down very much is in Europe. And the reason is that Europe at the time was very much controlled by the church. And the church said that nothing new could be made up in heaven. So they ignored that there was some new giant bright object up in the sky because it went against the Bible. So nobody really talked about it in Europe. Nobody wrote it down. They saw it. They just were told to ignore it. So they did. It's kind of a weird story. So maybe what Hubble should have said is, equipped with our 5 senses, along with telescopes and microscopes and mass spectrometers and particle accelerators and detectors across the electromagnetic spectrum, we explore the universe and call the adventure science. We can't do it with just our 5 senses. And now we're going to take a look at light waves in particular. If you could go ahead and write this question of the day down in your science journal. Just so you know, you are going to need a calculator for today. So go ahead and grab one of those. Just so that you know, a wave is nothing more than energy going from one place to another. Whether that's a sound wave, an ocean wave, a light wave, a gravity wave, it's simply energy that's traveling. That's all it is. What do waves travel through? Normally, waves travel through a medium. Ocean waves cause the water to go up and down. Sound waves cause air to contract and refract, and then contract and refract. So the medium for a sound wave is air. Electromagnetic waves are the only ones that can go through a vacuum. Electromagnetic waves are vibrations in the electromagnetic field, which exists throughout the entire universe. And so these can travel from the sun to Earth through the emptiness of space, whereas a sound wave would not be able to. And just so that you guys are aware, we can see visible light, but ultraviolet, X-rays, gamma rays, infrared, microwave, and radio waves are all parts of the same electromagnetic spectrum. And what makes red different than blue? Well, it has a different wavelength. What makes infrared different than visible light is a different wavelength. So infrared is technically nothing more than a different color than ultraviolet. And X-rays, just a color of light. Microwaves are a color of light. It simply has to do with the wavelength of light. Quick review of what a wavelength is. It's the length of a wave. To be a little bit more specific, it is from the crest back to the crest, or from a trough back to a trough, or the point from any part of a wave back to that same point on the next wave. It can be measured a lot of different ways, and all you need is a measurement of length. So kilometers, centimeters, millimeters, nanometers. Most light waves, especially for visible light, are measured in nanometers, which is a billionth of a meter. So you can have a billion of those right next to each other in 1 meter. Frequency. In math, that just means how often something happens. So frequency is how often a wave goes by you. So if you're looking at the peak of the wave, it's how often you see that peak pass by you each second. Frequency is measured in hertz. So if you have 1 wave go by in 1 second, that is 1 hertz. If you have 10 waves go by in 1 second, that's 10 hertz. You can have 1,000 waves go by you in 1 second, and that would be 1 kilohertz. If you had 1,000,000 waves go by you in a second, that's a megahertz. What I would like you guys to do, take a look at this one versus that one. For this particular wave, what is the frequency? Is it high or low? What is the wavelength, long or short? And what is the energy, high or low? When you compare it to this one is taller. And so a lot of people think that it has more energy. But the longer the wavelength, the lower the frequency, the less energy it has. Think of it this way. If you were standing in the ocean and you had a wave smash into you one time every second, that'd be a lot of energy being put into your body. But if you had waves smashing into you 1,000 times per second, that would be a lot more energy. So the more often a wave happens, the more energy it has, which means the higher a frequency of wave, the more energy it has. So this particular wave right here actually has a very low amount of energy. Now I want you to answer for this wave. Does this wave have a high or low frequency? Does it have a long or short wavelength? And does it have a high amount of energy or a low amount of energy? This one, because it happens more often, this one is going to have a much higher amount of energy, whereas this one has a low amount of energy. So this one has a low frequency, this one has a long wavelength, and it has a low energy. This one has a high frequency, a short wavelength, and a high energy. How fast do all of these travel? Does this travel the same speed as that? Well, all of them are electromagnetic waves. All of them are light waves. Every electromagnetic wave travels at the same speed, which is the speed of light, which is denoted by a little tiny letter c. And in fact, that's what c is in E equals mc squared. You might want to write this down. The speed of a wave is the product, so you're multiplying, the product of its wavelength times the frequency. I would write this equation down. Velocity equals the wavelength times the frequency. And for light waves, what is that velocity always and forever? It's the speed of light. Another way to write velocity is distance over time. You probably learned that back in middle school. All right, now that you have those written down, let's practice. Problem number 1, a tsunami wave travels at 150 kilometers per hour as it approaches land. If the wavelength is 50, what is the frequency of the wave? Well, let's go ahead and plug in what we know. A wave travels at 150 kilometers per hour. That is the velocity. So we're going to put 150 down. If the wavelength is 50 kilometers, so we're going to put down the wavelength. What is the frequency? Well, if you solve for f, you divide both sides by 50. And when you do that, you get 150 divided by 50 equals f. F equals 3. Problem number 2. A sound wave travels at 350 meters per second with a frequency of 500 hertz. What is the wavelength? Let's plug in what we know. The velocity is 350 meters per second. The frequency is 500 hertz. And now we're going to solve for the wavelength. How do we do that? Well, you divide both sides by 500. And when you do that, you get the wavelength equals 350 divided by 500, or 0.7 meters. We've got one more. A sunbather in Cocoa Beach is passing her time by counting waves as they break on the beach. She watches as one distant wave takes 10 seconds to travel 100 meters to the shore. What was the velocity of the wave in meters per second? Well, we're going to use the other equation. Velocity equals distance over time. We're asking what the velocity was, so hopefully it gives us the distance and the time. What was the time that it took? Well, it took 10 seconds. And how far did the wave travel? 100 meters. What is 100 divided by 10? The velocity is 10 meters per second. You guys are going to get to do something like this on your next test. Now go ahead and answer the question of the day that you wrote down a little while ago.